So the aim of this third part of the course is to try and talk in more detail about the technical underpinnings of Bitcoin and blockchain. So this is both more detailed and perhaps similar in spirit to how this module may have originally been advertised from the module description. Okay, but I think it's important to say here that this part of the course is softer in nature compared to the first quantitative part of the course, and I think this is probably more closely linked to, say, something like financial entrepreneurship than to hard quantitative finance. Okay, so there's slightly different emphasis compared to the first part of the module, slightly different to what you may have seen before. What I was trying to sort of get across here is that in terms of mastering fintech and certainly in terms of doing well on this module, what you need is a mix of different quantitative and qualitative skills, and the assessment for this module is intended to facilitate both those skills. Also, fintech and indeed finance more generally is, I think, different to and bigger than any individual discipline, so you need tools from different disciplines in order to have as broad a perspective as possible. So here a mix of hard quantitative skills related to the analysis of financial data and qualitative skills more closely linked to entrepreneurialism. So the fourth part of the course, in contrast to that, is a harder quantitative part. So one thing to emphasize here is that the quantitative modeling of market data from cryptocurrencies is a live topic of financial research. Okay, so there's this recently published paper by one of my former colleagues, Paraskevi Katsiampa, that has topped download and citations listings for the journal Economics Letters, and it's rather rare here that something I'm teaching even at MSc level is potentially so close to live academic research topics. I also wanted to introduce some work on the modelling of bubbles in cryptocurrency markets, which is where my interest in the subject originally came from. And importantly, historical economics and finance tells us that speculative bubbles are inevitable whenever new markets or new technologies are concerned. So what typically happens, if you look at this paper here by Zira in 1999, bubbles are often associated with either new technologies. You might think things like Bitcoin and blockchain, or an influx of new investors, e.g. cryptocurrency investors. Another thing here is that cryptocurrencies involve a sort of controversial separation from currencies and nation states, which means that bubbles are more likely to form and market prices may be more volatile as there's no monetary authority or equivalent to the Bank of England. However, there's a caveat that some people may think you can't define currencies as being distinct from a nation state in this way. So in terms of the layout of the rest of this lecture then, so we're talking about regression, and we're going to start with a big data example and then move to a small data example. So the first thing I wanted to say is that the big data example does come from a genuine industrial problem, an application to the electricity industry. So the things I wanted to emphasize here is that this isn't just something that you learn in college. Here we've got a genuine industrial problem that you need regression techniques of varying degrees of sophistication in order to get to grips with it. Okay, and it might look nice and easy now it's presented and hopefully taught well in this lecture and the next couple of lectures, but it wasn't necessarily a foregone conclusion at the time that a nice, neat and simple solution to this problem existed. And then the second problem I wanted to go through today is this small data example. So it's, say, they're conceptually interesting, but it represents a different challenge because the data is a lot smaller and a lot easier to manipulate. Okay, but I think it's useful to include this here because it gives you some extra practice on things like how to enter data in small problems, some extra practice with the coding and how to use R and get the results out, and also how to interpret them. Okay, and the name of the game with anything like this is always going to be communication. So we've got this motivating example then, which does come from a genuine industrial problem. So in regional monopolies such as electricity and water industries in the UK, customer satisfaction scores form the basis of regulatory fines. Now the whole system is potentially unfair if there is a detectable regional bias, i.e. in this case a regional effect over and above the actual level of service received. So what we're trying to do here is we want to try and measure regional bias using data from TripAdvisor, itself a big subject in its own right. So the data recorded are the hotel, the rating out of 5, the higher the better, and the region of the respondent. So in this lecture, the data are treated as if they are a continuous numerical variable, and so if they are, you can fit a regression model to them. Now this is quite a subtle point here, so this may not be actually strictly correct. So some mathematical people I know might wish to shoot me for being so imprecise here, but I think it does make it easier to use and interpret the model if you use this regression approach. Okay, so I think this is an important point to make here. It shows that aspects of the subject are maybe not purely mathematical, though they probably are inherently quantitative. But if they're not purely mathematical, there's a sort of common sense and interpretation angle which would wish to build into students. So we're going to start here by discussing an overly simple model for regional bias. So start with this regression model so that the score is related to some constant number alpha plus beta times the region plus some random error. And then there are, however, some subtleties here. So you have to bear in mind at this point that this is ultimately an overly simple model. Now, this is important to make this point because you can still make mistakes here, even if you are following what looks to be an intuitively reasonable looking approach. Okay, so this is quite dangerous. So for the moment, we ignore the effect of different hotels. So in practice, this is a simple mistake to make that would give dangerously plausible suggested answer to the question at hand, but it's technically incorrect because you haven't made an adjustment for this correlation caused by repeat measurements from the same hotel. But the basic idea in terms of the conceptualizing the model is that if the beta terms in the regression are significant, then we have statistical evidence of a regional effect, and the beta terms would also help us to quantify the practical effect of any regional bias. Okay, but the important point to make here is that you would need ultimately a more complicated version of this basic regression model in order to do this to a professional standard. We'll show you how to do that in lecture 3, but at least this thing is hopefully conceptually intuitive. So the usual way of testing significance in a regression model is to use a t-statistic, and the usual convention if you're doing this calculation by hand is that this thing is always positive. So you take the t-statistic to be equal to the absolute value of the estimate divided by the estimated standard error. Now sometimes this mathematical jargon can get in the way a bit. By absolute value I just mean the positive bit of it. So for instance the absolute value of -2 would just be 2, and then p-values are calculated automatically by computer, but work slightly differently if you're doing this calculation by hand. And I should say in the two equations on this slide, the second inequality is sign is pointing in a different way. So what you should have is that if t is bigger than 2.0, then this implies that p is less than 0.05, so the first line is correct. However, if t is less than 2.0, then p should actually be bigger than 0.05. So the important point is that if it's done correctly, the inequality signs point in a different way. So the first line is correct there, the second line isn't. So it can look confusing at first, it should become hopefully easier with practice. It turns out the easiest way to formulate this problem is to assume there is no effect or no relationship, and then look for evidence that contradicts this initial assumption, or what is called null hypothesis. But again, much of the terminology makes this look harder than it really is. I then give a quick note on p-values, and again remember that this thing is almost designed to look harder than it really is. So the easiest way to do this is to assume there's no effect and look for evidence that contradicts this null hypothesis. So the basic idea, if you have the score equal to alpha plus beta times a regional effect plus some random error, so if beta equals 0, the region does not affect the score. So, but if contrast, if beta is not equal to 0, then the region does affect the score. So the effect may be positive, so you may get a higher score if beta is greater than 0, or negative if beta is less than 0. And the important point is that low p-values, p less than 0.05, would be taken to be evidence against the null hypothesis. And then if, and only if, p is less than 0.25, you need to look at the sign of beta to see if the effect is positive or negative. So those two bullet points there with the low p-values and p being less than 0.05 is all you would need in terms of the interpretation, but in project work, especially dissertations, the interpretation can be a bit nuanced and a little unclear if, for instance, you have the p-value being bigger than 0.05 but less than 0.1. So in this case, this would usually be interpreted as weak evidence against the null hypothesis, but inconclusive and so hard to interpret in its own right. I'm here to just try and think about how any computational system is fundamentally working, and as far as R is concerned, just think R equals robot. Okay, so in R the computer will do exactly what you tell it to do, nothing more, nothing less. So actually in the longer term this makes it easier to understand what's going on, in contrast to things like Microsoft Excel. Now I'm not Superman, and this is the fundamental reason I don't wear my pants outside my trousers, okay, but Microsoft Excel is my sort of kryptonite. In contrast, I think R, besides because it does exactly what you tell it to do, nothing more, nothing less, it actually gets easier when you get more familiar with it, okay, but it can be a bit confusing when you're first starting out. So R is freeware and is freely downloadable, so do so, and especially this year with much teaching off campus, I think there's going to be increased emphasis on the use of freeware software. So this wasn't a problem at the University of Bradford last year, but I'm aware it has been a problem in some of my previous institutions. So sometimes R will actually work better on your own personal laptop than on a university computer system. And so because there's no security safeguards on your own personal machine, you may get more out of R's true functionality using your own laptop than a PC on the university network. Again, whenever you're using any computational system, it's worthwhile to think deeply about how the thing is working. So R works by referencing technical statistical terms defined by the mathematical theory. So you don't need to know the theory, but you need to be aware of this basic fact in order to understand how the thing is constructed and how it basically operates. So mathematically, regression models are known as the linear model, reference to my textbook there. So the basic R command is lm for linear model in order to reflect this. Now the basic structure of the syntax is the command is lm, it is applied to a y variable, and there is then a squiggle, which is a tilde, which means that the y variable is related to then a sequence of x variables that follows. So the default is that a constant term or intercept is automatically included in the regression equation, even though this is not explicitly stated above in the R syntax. Now the reason I mention this is that usually you automatically include an intercept term, but there are rare circumstances, like later in this lecture, where it is actually easier to fit the regression model without a constant term. Okay, this is the basic syntax that you use, and just be aware when you're looking at this syntax that this does have a mathematical underpinning. You don't need to know that, but awareness that there is a mathematical underpinning makes. Again, how is the thing working? Well, just think R equals robot. It will do exactly what you tell it to do, nothing more, nothing less. And as part of this, what you usually have is separate commands to run the analysis, where the command is lm, and then to display the results, where the command is summary. Okay, so again, R is like a robot. It will do exactly what you tell it to do, nothing more, nothing less. So the default in R is to fit a constant term, though this is not explicit in the R syntax. This can be suppressed using a -1 term in the sequence of x variables. I will show you that later in the lecture. Now, usually you almost always include a constant term, but occasionally it is easier to present results without this. And one of the things I was trying to say here is that you may be doing hard computing and hard maths, okay, but communication is always the name of the game. Okay, this can be quite subtle, and I would argue here this is one of the mistakes we arguably made in our published paper here in terms of how to present the results. Okay, so This caught out, in this instance, 2 professional statisticians, so this isn't necessarily completely trivial. Okay, so just to emphasize here, you may be doing hard maths and computing, but the name of the game is always communication.